Hi students, welcome back to geology. Here is our last little bit here on plate tectonics. We're going to look at interplate volcanism. Why does Hawaii ignore plate boundaries? The pondering question for this lecture or this video is, why might a volcano form in the middle of a plate rather than a boundary? I've given you lots of reasons why volcanoes might show up on convergent plate boundaries or divergent plate boundaries, but why might they show up in the middle of the plate? There's a number of examples here on this map. We're going to specifically focus on Hawaii this time around. So the theory of plate tectonics, again, we're looking back at the scientific theory that shows that Earth's lithosphere is comprised of a number of tectonic plates, and they've been moving for 3.4 billion years. Okay, the seismic network is what tells us where these boundaries are. This is all just review here from the last couple videos. And we want to now look at where volcanoes are sitting. Most of these volcanoes, again, are going to be sitting at the boundaries, but we have some exceptions. Hawaii doesn't exactly follow the rules. So we know that volcanoes come from rifting or pulling apart and from subduction. So the rifting being divergent plate boundaries and the subduction being the convergent plate boundaries. But then we also have these things called hotspots, which Hawaii is a great example of. And Hawaii isn't just a cool volcano, it also preserves plate motion for us. So a hotspot volcano is basically this plume of magma that is trying to push its way to the surface. It's finding any means possible to make its way to the surface. And so it's just a low density material that's trying to make its way to the surface. And it finds it through cracks and crevices in the Earth's crust and eventually deposits material. And this material can collect over time and create things like islands. And so that's where the Hawaiian Islands come from. But what happens is the Pacific plate isn't exactly stationary. So the hot spot is stationary, it doesn't move, but the plate does. So as the material is being added, the plate is still moving. So you can see in these diagrams, it shows the mantle plume or the hot spot producing material, and then the plate is moving in a different direction. The plate is actually moving in northwest direction today anyway. And it has created this chain of islands that shows you the linear transect of the hotspot. And the other thing that's really cool is it also shows us what the plate was doing over time. So the Emperor Seamount is part of this hotspot, which is north of the Hawaiian Islands. Most people think of the Hawaiian Islands as these just few islands, 5 or 6 islands that are really close to the Big Island. And the Big Island is where the hotspot is still active. And so over time, those islands that were over the hotspot got moved north and northwest. But you notice that where the Emperor Seamount begins and the Hawaiian Island chain begins, where those two meet, there is a shift in their orientation. The Hawaiian Islands are in a northwest orientation, and the Emperor Seamount is due north. And that's because around 40 million years ago, the age of that point, the Pacific plate started moving more in a northwest orientation instead of a north orientation. So there was a change in plate motion, which is what the hotspot records for us. Otherwise, we wouldn't have necessarily known that the plate changed direction slightly. So it ran into something that was more rigid, and it decided to start going a little bit further to the west instead of just north. Hawaii is not the only example that we have. In the middle of the North American plate, we also have the Yellowstone hotspot, which is a supervolcano. This hotspot is under thick continental plates, so it is really doing a lot of work trying to get up to the surface, because we're looking at 70 kilometers versus 30 kilometers thick of crust that it's pushing its way through. So the thick continental plate presents a much more difficult barrier for magma to penetrate. And what's really cool is that a lot of this material is connected to the much older Columbia River basalt, and that looks to be about 70 million years old. So again, this is a hot spot that is a magma plume forcing its way to the surface, and it's not at a plate boundary, it's in the middle of a tectonic plate. So as I said in the last video, remember, this is dynamic. This is always changing. What we see today is not what we're going to see in a million years if we're still around. And it's certainly not what we saw a million years prior. So your final thoughts for this video is explain in one sentence how hotspot reveals plate motion and records it for us. I will see you guys in the next set of videos. Take care.